before we get on to the next few concepts, we want to talk about orientation of a surface. So you have some surface. This is my generic way of writing that surface, right? Then a surface S, so this is my surface S, is oriented if a unit normal exists at every boundary point and S has two sides. So basically you have some normal, some unit normal vector, and there's basically an up and a down, or top and bottom, right or left. So it has two sides. So a good example of something that does not have sides is called a Mobius strip. So look that up and see what that is. Basically, if you take a thin piece of, take a piece of paper, cut it in a strip about maybe an inch and a half, maybe an inch, lengthwise, and then you do one twist and connect it with a staple, and that has only one side. If you start on one side and go around to the other, you will not change sides. So that is not what we call an orientable surface. So we want to, that's part of the hypothesis later of some of the theorems. Suppose S is given by Z equal to G of XY. Then capital G can be written like this, equal to 0, just set it equal to 0. Then we say S is oriented by N, where you do this, you basically take the gradient, which gives you the normal, and then you unitize it, divide by the magnitude. So we'll be using these equations to do an upward normal and downward normal. We don't really need to care much about it when we do them, but that's how they're done. If you have a surface S defined by R of UV, so you have X, Y, and Z all in terms of UV, then N is you still do the cross product. That gives you the normal, and then you make it a unit vector. So it makes it into your vector N. Okay, then we want to talk about the concept of flux, or a flux integral. So we want to picture a vector field. So think of F as a velocity field. So here's my F, like this. So F is going through the surface. I'm going to picture it going through the surface somehow. Then we can calculate F dot N, and then times the area of the little patch or the surface. And that gives you kind of like the amount of the flux. That's the amount of the velocity that passes through the surface. So that's called flux. Okay, so this is the definition. So this is it's a surface integral. So you're integrating over the surface S, and F dot N calculates kind of like the amount that's going through it. So if you have perpendicular vectors, then you're going to have a greater amount because you're not wasting the amount of geometry. Doesn't gives you more stuff there. So when you do this, you're looking at the ds is this little patch, and then here's your vector. And then you're basically calculating this volume of this prism when you do that calculation. Okay, so that was very brief. So look that up more and look up flux or flux integral. What we use, though, are the evaluation formulas. Okay, so we say the surface S is oriented by N, and then you have Z equal to G of XY. And then this you can calculate. This not so much because it's ds. So usually we use the two ones I highlighted here. So you do F dot and then you do the partials, make them negative, and then of course for Z that's just going to be 1. If your surface is given in terms of r of uv instead. So now this is S. So if that's my S, then we can use R. You do it. So this is in, because you do the cross product divided by the magnitude. But ds is the magnitude dA. So these reduce, and you end up with F dot, the cross product of partial RU, partial RV. And so those two are your evaluation formulas. That's what you're actually going to use to calculate the flux. So let's look at this example. Find the flux through S. So S is given by this surface. So what type of surface is that? Okay, that's a sphere in the first octant. So, that's what they want to calculate the flux in the first octant. So it's a sphere, but we're going to reduce it to the first octant. The vector field is given by kind of the simple one. We've done something similar before, x, y, z. Okay, so then for S, I change that into a radical. So I just solve for z, and you take the top portion. So that's the upper part, and then we're just going to take the positive xy axis. So g of x, y, z is this. Right, so you just set equal to 0. So you can say like this is equal to 0, but it does not really matter. Then you do the partials. So I'll leave this to you. This is a little bit of algebra to work out. Okay, so down to here, I guess. So do the partials, or do the gradient of capital G, and you get this. You get this. So you're doing the partials on Z. Okay, then you do the dot product. Usually you make the dots a little bigger there, huh? So then you do the dot product with F. All right, so F is your X, Y, Z. That's where you get your values in there. Here's X, and you get times X, times Y, and then times Z. Add that up, and then you have this form. Okay, and that simplifies again down to here. So your flux is F dot in ds, which is actually F dot gradient of G dA. So this is what we're going to use right here, and then it's dA. So our region in the xy plane is this. So that's my R. And so when z is 0, you get x squared plus y squared equal to 4 squared. So you might as well use polar there, or cylindrical, basically. So you evaluate this, and don't forget your extra r, 16r, and then it's dr d theta. So evaluate this and see if you can get 32 pi. The next couple theorems we'll be using finding flux, basically, or you can, by applying the theorems. The next theorem is called Stokes' theorem. So for Stokes' theorem, C is a piecewise smooth, simple closed curve. Okay, so here's my C. Okay, C is up here, like that. Okay, and it's does not cross itself, and it's smooth. Okay, F is my vector field. So F is some field that goes like this. Oops, I'm going to change the color on that. Okay, so here's my F, and it does like pass through the surface. So we want to picture the vector field, the velocity field, acting on something on that curve. So it's like acting on the particles on that curve, or something on this curve like this. So the curve is the boundary of this surface S. So look at this formula down here. Here's this S is this S here. And so that's the boundary of this. So the line integral over the curve like this, with F acting on it, is F dot dr. Okay, so that's a line integral of the curve, or around the curve. That is equal to the double integral over the surface, this entire surface, of the curl of f dot in ds. And we'll have to look at an evaluation formula for that, but you do the curl of f, dot it with these within. So you can go either evaluate this or evaluate this one. And so there's a lot more to that and how to prove that, but there's what it's looking at. Basically, if you add up all the little curls up on the surface, think of those little things. If you add all those up, it's the same as looking at the general tendency of the circulation around the curve. So however the function or the vector field is acting on it, it's making all these little swirls up on the surface. And if you add all those up, which is basically this concept, it's the same as if you just added up what is on the curve. And again, there's a lot to that, but okay. So just to apply it, you can either apply, just do the line integral or do this, depending on what the question is. So use Stokes' theorem to evaluate the line integral if f is x, y, z, y, and z. And s is given by the first octant portion of z equals x squared over this region. Okay, so let's take a look at that one. So f is given. So you want to actually calculate this line integral. So, so we're given s, and you want to basically look at the intersection of s that's over x squared plus y squared equal to a squared. All right, so then, what is that? I was looking at my work there. Okay. So then g then is z minus x squared. So that is this. So g of x, y, z is, you just set this equal to 0. Then you do the gradient, okay, and you get this. All right, so these are the two hypotheses we have to have. G has continuous first partials, and C is a piecewise smooth, simple closed curve. So you would have to state those hypotheses to confirm that. So, so what is z equals x squared? That's basically a parabola that goes out along the y-axis, and then so it's above this region. And I don't have that diagram. I guess I should have. Okay, so maybe see if I can do this over here somewhere. So in 3D, you're going to have something like this. So here's x, y, and z. So z equals x squared, so that's basically a parabola like this, and then it goes that way. Okay, so it's a parabola that goes out, so y is arbitrary, and then you're below or above that, so this goes up to the surface. Okay, very rough diagram, I know. All right, so then we can apply Stokes' theorem instead of integrating around the curve, which we don't even really know. Like, we would have to define what that curve is. We just can kind of picture that it will be a simple closed curve. So instead, we can integrate over the surface. So you just go up to the surface using the region R. So the curl of f, we calculate and get this. Oops, I meant to do that and that. The curl of f, we evaluate and get this. Then the line integral is the curl of f dot s, and then I went ahead and put this in the parametric form or the component form of your negative x z dA and negative x cubed dA. So that's over the region R. So this is your region R that we're talking about. Okay, so now once you're down to this step, the rest is just like we've done before. So getting from here to here takes a little bit of work. Look up kind of what that does and how you get. This basically is another function. This is like I don't know, h or something. This is h dot in ds. So this is like flux. It's just we're doing curl of the given velocity field. Okay, so you can look up how you get from f dot n ds or like h dot n ds to this form. Okay, then you evaluate, and I don't have the solution, but critical aspect really is to get to basically here. Okay, last theorem is called the divergence theorem. This one, frankly, is a little bit easier to use. I like this one better. It's a little more simple, I think, less kind of weird. The Stokes theorem is always kind of strange to look at. This one, I think, is a little more concrete. All right, so let Q be a solid bounded by a closed surface S, oriented by an outward unit normal N. F is a vector field with continuous first partials. Okay, then, so it's a closed surface, keep that in mind. Then the double integral over S of f dot n ds, so that's basically flux through the surface, is equal to the triple integral, basically like volume, of the divergence of f dv. So you take the divergence, sometimes can make that a lot easier, and then it's just dv. So you don't have to deal with the ds part. You don't have to deal with converting what that is. You just take the divergence and do a triple integral over the volume. So it's a much more elegant way, often, to simplify things. So suppose f is m n p. Then the divergence, which I don't know if we talked about that before, but divergence is you do the partials and you just add them all up. We did that, yeah. So divergence, remember, is a scalar function. So when you do divergence of f, you're not getting a vector, you're getting a scalar. So these are functions of m, n, and p are functions of x, y, and z, and then you do those individual partials and then add them all up. So let's look at this example. Calculate the flux, f dot n ds. Okay, and this at first really shouldn't be here. Let me get rid of that. Okay, so calculate the flux like that, where f is given to be this entire thing, and z is this surface, which I have sketched below. 1 minus x squared is equals 0, 0, and y plus z equals 2. So this is a paraboloid. Or no, it's a cylinder, right? So this is the cylinder, a parabola, that goes out along the y-axis like this. So here's your parabola, like this, upside down. Remember the other one was the other way around, the one we just did. And then this just means the planes, right? So you're cut off by the back and the bottom, okay? And then this is a plane. So what you do is you draw the line in the zy plane like that. So it's like this line. And so it's going to cut off that surface like this. So to calculate the flux, you can then almost always, this is what we do. We calculate the triple integral of the divergence of f. And it becomes much easier. So if you do the divergence of f, and it could become more complicated, granted, but that's kind of not the point usually. You get a much simpler function. You get just 3y. So you got to state the hypothesis here. This is critical when you're doing these questions, is to state the hypothesis. So to be blunt, points will be taken off. So Q is a closed surface. F has continuous first partials, and you don't have to prove that. You just state it usually. I mean, it's a polynomial. It's got continuous first partials. If that's the case, then we may apply divergence theorem. So that's where the star came from. So this, the flux is equal to, and then you got to figure out how to do that calculation. And I went from y equals 0 out to the surface, which is 2 minus z, because you just solve this for y. So y equals 0 to y equals 2 minus z. And then we integrate from 0 up to 1 minus x squared, like that. So there's your representative rectangle, like that. Okay, and then you go from -1, which is here, to 1, or vice versa. -1, which is there, to 1, which is here. I showed that step here. Okay, so look up how to do that, or spend some time making sure that makes sense. You do your integral, and I didn't get the solution, but these are just polynomials, so really no big deal to simplify that. Okay, so that was all of chapter 16, very much in brief.